Yes, sir.
So in those two recorded lectures, I started some discussion on transducers, different types of transducers. So some advantages of using electrical transducers were discussed. That what is the advantage if we convert a non-physical, non-electrical quantity into an electrical quantity. Then there were some classifications shown how the different types of transducers can be classified into different categories. After that, our discussion was on three types of resistive transducers, which included strain gauge, then the RTDs, resistive temperature detectors, and thermistors. So I ask you guys to go through those lecture videos, and uh, if you have any questions, most of you have, I believe that maybe you haven't gone through the videos. If you have any question or any query, you can uh, email me. I'll try to respond. And in today's class, mostly I am going to discuss about some basics of inductive and capacitive transducers or their working principle. So if I start with the inductive transducers, so they basically work following the principles of change in self-inductance or change in mutual inductance or by the production of eddy currents. So if we focus on the I mean how an inductive transducer can be uh, established or formulated with respect to the variation of self-inductance, then we can focus on the relation of self-inductance that is shown over here. So in this expression, the capital N indicates the number of turns in an inductive coil. Mu represents the permeability of the magnetic path, and A is the cross-sectional area of the magnetic path, and L indicates the average length of the magnetic path. So with respect to this particular expression, it can be suggested that uh, the self-inductance L is actually a function of all uh, these four quantities. So if any one of these four quantities can be varied with respect to the variation in some physical quantity, then the self-inductance will change, and in that way the physical quantity can be transferred or transformed into the change in self-inductance. So how we normally get this sort of an equation, or we can derive this sort of an equation. So if we consider an inductive coil, suppose the coil is carrying current I, so it will generate some MMF, also it will induce some uh, voltage, and the flux which is generated due to the change of current, we can denote it to be phi, and the self-inductance is basically the voltage, the property for which the voltage is induced in the coil itself. And mutual inductance is, that if the voltage is induced in any other nearby coil due to the current flow in another coil, then that is the phenomena is called a result of mutual inductance. Now for self-inductance, the voltage induced in the coil, we can easily write it in this form, which you all know, that is L di by dt, and the negative sign has to be included there according to the Lenz's law, because uh, the induced voltage is going to oppose the rate of change of current. Now, apart from this, the same expression can be written in terms of the change of flux and the number of turns. So with respect to that, according to Faraday's law, with respect to the change of flux, the same induced EMF can be represented by the change of flux and multiplied by the total number of turns in the coil. So from here, if these two expressions are equated, then it can be easily written like this, and from here later on, if you integrate for a specific time duration, then you will actually have this sort of a relation between the total number of turns, the magnetic flux produced, and the current which is flowing through the coil. To further elaborate this expression and to determine this particular relation of self-inductance, we can uh, work with phi, and for that we can define phi with respect to the mutual flux density. So the magnetic flux density B, you know that it is the magnetic flux which is flowing through the per unit area of a coil at the right angles. So from here we can say that magnetic flux will be the multiplication of the magnetic flux density and the cross-sectional area. So in this relation we can replace B with this expression mu into H multiplied by A. So you know B is equals to mu into H, where mu is the permeability of the magnetic path. So the permeability of the magnetic path actually uh, indicates the ability of the magnetic material to support the development of magnetic field inside it, and H is the magnetic field strength or magnetic field intensity, which is proportional to the current, and the proportionality constant is often defined as the number of turns of the coil per unit length, and the unit is often represented as amperes per meters or ampere turns per meter. So if this expression of H is written over here, then we have N mu I into A divided by L. So that is our phi, and from this equation now, if we put the value of expression of phi, that will further reduce to the expression which is shown over here. So from this expression you can say that L is the function of the number of turns, the magnetic permeability, the cross-sectional area, and the average length of the magnetic path. So the physical quantity that you want to measure, if that physical quantity is transferred into change of any one of these quantities, so that will eventually result in the change in self-inductance. So another term for magnetic circuits is very common, which is the reluctance, which is analogous to the resistance. Now reluctance, you know that it is the opposition offered to the magnetic flux or the resistance that the magnetic flux experiences in a magnetic circuit, and it is denoted through this expression. Now the reluctance is also a function of the length, the cross-sectional area, and the permeability. If these quantities are changed, one or more of these quantities, then the reluctance will also change, which will eventually result in the change of self-inductance. So with respect to that, one way of having a inductive transducer could be by varying or changing the number of turns of the coil. So this operation is or mechanism is quite similar to the mechanism of linear potentiometers or rotary potentiometers. From the two symbols or simplified diagrams shown in figure A and figure B over here, you can easily also suggest that the figures are almost similar to the figures you see for a linear potentiometer or a rotary potentiometer. So here we have two fixed terminals, suppose, as I have highlighted here. So within these two fixed terminals, there is total n number of turns of the coil. And apart from the two fixed terminals, there is a movable terminal as well. So this sliding terminal or movable terminal can be moved along the entire coil. So depending on the position of the position of this moving contact, the effective number of turns will vary from suppose 0 to n. So with respect to that, your inductance from this point up to this one will also change from 0 to up to the maximum limit, which is for the total number of turns of n. So in this way, if this moving arm is supposed coupled with some other mechanical transducer, which would result in the displacement of this movable arm, then that how much displacement has took place, that can be predicted by the change of the value of the self inductance. And if the movable arm moves back and forth, the effective number of turns of the coil will change, and that will eventually result in the change of self inductance. Similarly, for angular inductive transducer as well, there are two fixed terminals. So among these two fixed terminals, there is suppose n number of turns in total, and depending upon the position of the movable wiper, which in this case can rotate in clockwise or anti-clockwise direction. So how much rotation it has, uh, by how much degree it has rotated, that can be predicted by the value of the uh, self-inductance. So for example, if the total winding of the coil is corresponding to suppose the total n number of turns, the inductance corresponding to the total n number of turns here may represent 360 degrees. So how much actually you are getting between a fixed terminal and the movable terminal, how much inductance you are getting, or maybe the effective number of turns might be n1 up to this position. So n1 by n equals the unknown value that you want, or angle that you want to determine, divided by 360 degree. So in that sense, the uh, um, uh, prediction of the angular displacement can be done. So suppose at this point it is maybe 0 degree, and at this point when you are taking the entire number of turns, it is 360 degrees, and for any intermediate position of the sliding contact, the corresponding angular difference can be predicted as well. Now another way could be varying the permeability, because the self-inductance is also a function of permeability as shown in the previous slide. So if you have a coil arrangement, if you can change the permeability of the magnetic path by some way, then that will also result in the change of self-inductance. So for example, here the winding of the coil is done in a cylindrical tube, where the uh, a tube is hollow. It is a hollow tube, so inside the tube you can actually insert some magnetic material. So for example, when there is nothing, when the tube is hollow, you can say that there is only uh, uh, nothing but air. So for that you can say that the magnetic permeability will be mu naught, which is normally 4 pi into 10 to the power minus 7. Now when you are inserting an iron core or any other ferromagnetic core, depending upon the relative permeability of that particular magnetic material, your overall magnetic permeability will also change. So if any linear displacement in any physical quantity can be coupled with this shaft of this iron core through some maybe some mechanical transducer, so that will convert the physical uh, quantity, the variation in the physical quantity into variation of in terms of displacement, so that that displacement will be transferred, or motion will be transferred into this shaft of the iron core. So depending upon how much displacement is taking place, a portion or the entire iron core might be inserted into this hollow tube. So depending upon how much iron core is getting inserted into the hollow tube, the overall or effective permeability will cause the value of the self-inductance to change. So in this way, through multiple stages, ultimately the physical quantity can be transferred into with respect to the change in self-inductance. Similarly, we can also have uh, inductive transducers by the mechanism of varying reluctance. Now, varying reluctance or varying permeability, they are actually interrelated, because as the reluctance is also a function of permeability. So whenever there is change in permeability, there is supposed to be change in the reluctance as well. Now, the arrangement, the simple arrangement which is shown over here. Here, first of all, a ferromagnetic core material is shown, over which the winding of the coil is done. Now, the ferromagnetic core is separated into two parts. So one is the fixed portion, another one is the movable portion or the armature. So the movable armature can be linearly displaced back and forth or left to right, and depending upon that, the reluctance of the magnetic path will change, because suppose when this core is located at the extreme right, or the extreme point is in contact with this fixed core. So when this movable core is in contact with the fixed core, then there is supposed to be no air gap. So this air gap is not supposed to be present in that case. So the entire magnetic path will then have the ferromagnetic core, and for that instant there will be a specific value for the self-inductance developed in the coil. However, when this armature shifts from these 2 points of the static ferromagnetic core, so as it is going to shift more towards the left hand side, the air gap will increase. So as the air gap is getting increased, so apart from the ferromagnetic core, also the air gap will introduce change in the overall permeability of the magnetic path. So the permeability will change, and also the length of the magnetic path will also change due to the presence of the air gap. So as these two quantities are changed, both of them are related to reluctance, or reluctance is dependent on both of them. So the reluctance will also change. So in that sense, you can say that this sort of arrangement can be termed as an inductive transducer obtained through variation of reluctance. However, the previous arrangement, you can also term it as a variable reluctance type transducer, because obviously when the permeability is changing, the reluctance is supposed to be changed. Now, here we are going to discuss about a more practical type of inductive transducer, which is used for different applications. Now, it actually operates in through the principle of change in mutual inductance between two coils. Now, the device is called linear variable differential transformers, and the short form is LVDT. So mostly it is used to predict any linear displacement with respect to uh, the change in mutual inductance. So the linear displacement is first transferred into change in self-inductance, and later on the the linear displacement is transferred into change in mutual inductance that will eventually give us the output in the form of change in voltage levels or change in induced voltages. So before going to the operating principle, we should discuss something about the construction of this sort of a transducer. So as this is it operates through a differential transformer mechanism, you can say that obviously there is supposed to be some primary windings and some secondary windings, which which is normally the case in this structure of LVDT. So this is a 3D view, and a cross-sectional view is presented over here. So the primary winding is placed at the center, and on both sides of the primary winding, two secondary coils are placed as well. So the windings and the materials used for both the secondary windings are identical. However, they are connected in series opposition so that the voltage difference between the two coils can be taken as the output. And the windings are actually done in actually a magnetic core material, and inside the cylindrical magnetic core or former, a hollow space is there where an iron core can be, or any ferromagnetic core can be inserted. So this is that iron core, or this one. And this is the primary winding. This is suppose secondary winding 1. This is secondary winding 2. Now, if we want to talk about the working principle, then we can refer to the next slide, where the same LVDT is shown in terms of circuit symbols. So as I have already said that there are 3 windings in total. One is the primary winding, and there are 2 secondary windings, suppose secondary winding 1 and secondary winding 2. So whenever you're going to supply any alternating voltage to the primary winding, there will be some magnetic field produced in the primary winding, so that will induce voltages in the secondary windings depending on the mutual inductance developed in both the windings. So with respect to that, the output will be taken as the difference between the voltages induced in both the secondary windings. So that is why the secondary windings are connected in series, but in series opposition. That is normally said in this sort of cases, because we are not just connecting them in series like this, because if we connect them in this form, then we are not going to get the differential output. Rather, we are going to get the summation of both the voltages, which is induced in S1 and S2. So that's why they are connected in series opposition like this, and the outputs are taken from these two terminals, so that the output could be the difference between the two voltages, which is induced in S1 and S2. Now, for the primary winding, the voltage and the current relation can be related through this. If we consider that Rp is the parasitic resistance present in this primary winding, and Lp di by dt is the voltage developed across the primary winding due to the self-inductance in the primary winding, then the input voltage can be related with respect to this expression. Now our concern is the development of the induced voltages in the secondary windings. So those induced voltages V1 and V2 can be represented in terms of the mutual inductance in both the windings and the corresponding rate of change of current. And the output voltage is the difference between the two. So the rate of change of current in the primary winding is the same. So if there is a mechanism that is going to cause the change in the mutual inductance in both the windings S1 and S2. So with respect to the change in the mutual inductances, the output voltage will vary. So in order to have some change in this mutual inductance, the iron core is placed over here. So if the iron core is moving back and forth, then it is actually going to cause the mutual inductances between the two coils to be changing. Because suppose when the iron core is placed at the center in such a way that both S1 and S2 is getting equal share of the iron core with respect to the primary winding, then the magnetic permeability for both the primary winding P and S1 and the primary winding P and S2 will be identical. So the induced voltages at V1 and V2 will be also same. However, if the iron core moves upwards, so the magnetic permeability of the path between uh, primary winding and the secondary winding 1 will be more compared to the permeability of the magnetic path between the primary winding and the other secondary coil. So in that sense, if the core is moved upwards according to this diagram, so more magnetic coupling will be there between the primary winding and the top coil. So the voltage induced mutual inductance in the uh, top secondary coil will be more compared to the secondary coil 2. So the voltage V1 will also be higher compared to voltage V2. So in this case, the output voltage will be positive. Now at the null point, null position, both the mutual inductances are going to be same because the coupling between the primary windings and the two secondary windings are same. So the output voltage will be 0. And if it is moved downwards, then the voltage V2 will be greater than V1, and in that case the output voltage will be less than 0. So in this way, the change in M1 and M2, the difference between them is linearly related to the core displacement. However, the linearity is normally obtained for a certain range. Now if I go to the next slide, so suppose here the relation between the displacement and the output voltage is shown. So with respect to the displacement, whether the output voltage will increase or decrease, that is shown in this figure. So we can first of all consider 3 points. Suppose let us start with the null point, which is indicated at the origin of the two axes. So the null point is when the iron core is placed at the center, so that both the windings are getting the equal share. So even if you are providing alternating voltage at the primary side, at the secondary side the differential output will be 0 as indicated over here, and that can be also represented through this point highlighted over the axis. Now as the core moves towards the right hand side, so the coupling with the primary winding and the secondary winding 1 will start increasing. So as a result, V1 will start increasing compared to V2, and the output voltage will start becoming more and more positive, which is indicated through this line. So the output voltage will gradually increase with the increase in the displacement of the iron core towards the secondary coil 1. And as we move the iron core towards the secondary coil, suppose there would be a position when the secondary coil 2 is not getting any shear of the iron core or magnetic core, then that point can be defined here as the point B. So if you if we move the iron core beyond this point, then the variation becomes a non-linear and it almost gets saturated. And if we consider the phase, so as V1 is greater than V2, so V out is going to be positive, and for this portion of the movement of the iron core, the phase difference between the output and the input is 0 because they are in phase. So if the same y-axis is used to represent the phase difference between the input and the output, then that can be just represented through this horizontal line. Now, similarly, if we consider that the iron core is moving towards the left hand side, so if it is moving towards the left hand side, the coupling with S2 will start increasing. So V2 will be greater than V1 now. So V out will start to become negative, and as a result, the output voltage will start decreasing now up to a certain point. Then it will again start getting a non-linear variation, and at a point it will become saturated. And if we talk about the phase difference, then for this case the phase difference will be 180-degree phase shift between the input and the output. So that can be represented by this line that is indicated over here. So this is the general characteristics of the LVDT. Now the focus is to operate the LVDT within this linear range of operation. Then the variation can be easily predicted through the simple linear relationship between the change in displacement with respect to the change in output voltage. Now if I briefly highlight the different forms of energy conversion that is taking place. So for the first case, any physical quantity has to be first detected by some sensing element, and that has to be converted into displacement. Displacement or linear motion, I can say. Then that has to be transferred into the iron core of the LVDT. So if it is transferred to the iron core of the LVDT, it causes change in mutual inductance. And as the mutual inductance is changing, and with respect to that, as we are taking the differential output, so the final form of the energy that we are getting is the voltage difference or differential voltage. So for measuring any physical change in any physical quantity, this sort of energy conversion will normally take place in case of LVDT. Now these two portions are actually taking place in the LVDT. However, this two portion has to be done by some other primary sensing element. It could be mostly it could be a mechanical transducer that is going to primarily sense the change in the quantity. It could be pressure, force, flow, or velocity, and then it will transfer it into displacement or linear motion, which can be coupled with the core of the LVDT. So the advantages of LVDT is highlighted over here, that it has a linear range of operation up to 5 millimeters. Then the output voltage that we are getting, that is significantly high in magnitude. So there is no necessity of using a separate amplifier circuit to amplify the output voltage further. Sensitivity is also high. So here the sensitivity is the change in voltage with respect to the change in displacement. So a 40 volts per 1 millimeter change uh, in the displacement of the iron core can be obtained. So this is a quite high sensitivity that can be obtained through the LVDTs, and their construction is also rugged and robust, so they can tolerate a high degree of shock and vibration. And as the movable iron core is not having any direct contact with any of the primary or the secondary windings, so it is moving in a hollow tube, so it is less prone to errors or wear and tear resulted due to friction. And also it can be operated at a lower power level, so the power consumption is also less. Now, where LVDT is used for uh, detecting linear variation or linear displacement to predict the rotational changes or angular displacements, rotary variable differential transformer uh, can be used. Now, the working principle is same. As the output, we are taking the differential voltage between the two secondary coils as indicated over here. So if it is secondary coil 1, secondary coil 2, so similar to LVDT, where there is a primary winding to secondary windings, and the output is the differential voltage between the two secondary windings. However, the difference is that the ferromagnetic core or the armature is now going to move in angular direction rather than in linear motion. So with respect to the angular displacement in the armature, the induced voltage or the will change due to the change in mutual inductance in both the secondary windings because of the change in the magnetic permeability between the paths. Now, a general construction can consist of a E-shaped iron core or ferromagnetic core. So in the central leg, there could be the primary winding, and in the other two legs, there could be the two secondary windings. And with respect to these static coils, three static coils, there would be an armature or movable core which can rotate through this pivot or centering this pivotal point. So for this sort of rotary variable differential transformers, the characteristics of the angular displacement to the change in voltage would be linear or can be established to be linear up to 40 degrees, plus minus 40 degrees. So up to this amount of angular displacement, it can be used with a linear relationship. Okay. Now, if I move on to the variable capacitance transducers, so similarly, like we examined the expression of uh, inductance first. So, what are the variables upon which the inductance is related? So, in case of capacitance, or if we consider parallel plate capacitor, it is actually a function of three quantities. You know that the permittivity, then the area of overlap between the two plates, and the distance between the two capacitive plates. So in case of capacitance, if any one of these three quantities is varied, then that will eventually result in the variation of the value of the capacitance, which can be used to predict the change in any particular quantity. Now, so the first type of capacitive transducers can be formed with respect to the distance between the two plates. Now, for this sort of capacitive transducers, it can be considered that the two plates Suppose this is the upper plate, this is the lower plate. So for these two plates, the area of overlap will be the same for the entire duration. Then the dielectric material will also be the same. However, the upper plate can be moved in vertical direction so that the distance between the two plates may change. For that, epsilon and a can be considered to be constant, and the capacitance can be represented as a function of x, which is the displacement between the two plates, or distance between the two plates in this case. Then this will be the expression for the capacitance between the two plates, and epsilon r could be the relative permittivity of the dielectric material. Now, if this equation is differentiated with respect to x, then that would give a measure of the sensitivity. So then after differentiating the previous equation with respect to x, this sort of an expression can be obtained. So dc actually represents the change in capacitance with respect to the change in displacement. So this is actually going to give a measure of the sensitivity with respect to the variable x in this case, because these quantities are fixed or constant for a particular arrangement. Now if x is varying, then with respect to x, what would be the sensitivity that could be predicted? Now if the same equation is rewritten, suppose epsilon r epsilon naught a by x into 1 by x, so this is actually c itself. So the same equation can be rewritten in this form. So where it can be seen that the per unit change in capacitance is proportional to the per unit change in x. So any small incremental displacement can be actually predicted directly or in proportion to the change in capacitance. The other type of capacitive transducer may be formed by varying the area, overlapping area between the two plates, the upper plate and the lower plate. So for that reason, in this case, it has to be considered that the uh, permittivity of the dielectric material will remain constant, and also the distance between the two plates will remain constant, but there will be change only in the overlapping area. So if the bottom plate is considered to be the fixed plate and the upper plate is considered to be the moving plate, now instead of vertical displacement, now if we consider horizontal displacement as indicated over here, then that will actually eventually cause the change in overlapping area, because now this would be the portion of overlap between the two plates. So we are going to lose some of the uh, area due to the horizontal displacement. So that horizontal displacement is represented here by x. So if W is the width of the upper plate, then the area that we are going to lose is Wx as indicated by here in this equation, and the capacitance is simply represented over here. So this horizontal displacement x is actually causing the change in uh, overlapping area. So if you differentiate this expression with respect to x, so this x is actually now the horizontal displacement, not the vertical one like before. So if you have or take the derivative of this equation with respect to x, then in terms of the horizontal displacement, you can have a measure of the sensitivity of this sort of sensor or transducer. Now, lastly, the variable dielectric displacement sensors, which is, you can easily say that now the overlapping area and the distance between the two plates will be fixed. However, the position of the dielectric material will be changed, and with respect to that, the capacitance will change as well. So the displacement may be done with respect to some change in some physical phenomena. Now, before there was any displacement, suppose the dielectric can be displaced in horizontal direction. Now, before there was any displacement when x was equals to 0, so this would be the simple expression of the initial capacitance, where W is the width and L is the length of the uh, length of the entire arrangement actually. So whenever there is a displacement in the dielectric material, so suppose the dielectric material has a relative uh, permittivity of epsilon 2 and the or epsilon 1 you can say, and the portion that is not containing this dielectric material due to the displacement x, that for that let us consider that the uh, permittivity is epsilon 2. So in that case we can rewrite both the equation of capacitance with respect to both the permittivities, and for epsilon 1 the effective area will be A minus delta A, and epsilon 2 the effective area will be delta A. So the delta A is nothing but W into X. So with respect to that, the value of the capacitance for any non-zero value of X can be written in this form, and from here uh, the expressions can be rearranged in such a way that eventually you will get uh, the expression to have a linear relationship like this, because this amount is actually a constant, then this almost corresponds to, or this corresponds to, suppose the slope, and this is the variable. So in that sense the capacitance can be linearly related with the displacement x of the dielectric material. So further it can be simplified to be the initial capacitance at when x equals to 0 and the change in capacitance, which is this one. So this could be the three possible cases where the three types of variable capacitive transducers can be developed, keeping these three phenomena in mind. Now, like LVDT, it is often uh, useful to have differential arrangements of capacitive transducers as well. So for capacitive transducers, similar to LVDT, like the differential the output was the differential voltage between the two secondary coils. So here for capacitive transducers, if also differential arrangements can be done where the final output would be in the form of a differential voltage, then it becomes easier to further the uh, process the output in which is actually in form of obtained in form of change in voltage that could be easily amplified, or other signal conditioning operations can be easily done when the output is extracted in terms of change in voltage. So different arrangements can be there for differential for forming differential capacitance. So similarly they can be done through the uh, through varying the area of overlap, or varying the distance between the uh, multiple plates, and by varying the dielectric between the different plates. So Figure A shows an example of differential arrangement of capacitors by varying the area of overlap. Figure B represents the arrangement which is based on the varying the distance between multiple plates. And lastly, this one represents the variation with respect to the dielectric constant. Now, for all the arrangements, suppose for the first one, these two plates are considered to be static, and the upper plate is considered to be a movable plate which can move to the left or right. And as it is moving to the left and right, the area of overlap between the two static plates will change depending on the direction of the movement. So if it is moving on the right hand side, the area of overlap between the upper plate and the this static plate will increase, so the capacitance will also increase. And similarly, if it is moved on the left hand side, the capacitance developed within the upper plate and the other secondary, other static plate will increase in that case. And if it is located at a null point where both the static plates are having equal overlapping area, so in that case the capacitance value will be equal. Now for this sort of a differential arrangement of capacitive transducer, the use of a particular AC bridge circuits might be useful. So if the differential arrangement of the capacitor is connected in this way in a AC bridge circuit, so suppose there would be a capacitance between the upper plate and this fixed plate. Let me denote it as suppose C1, and there will be another capacitance C2. So this C1 and C2 is actually forming the two arms of the AC bridge, and for the other two arms there are two resistances connected. So in the schematic diagram I can say that this is C1, this is C2. So when the movable plate is located at the center, so that both the bottom plates are getting equal overlapping area with the upper plate, then suppose the bridge is balanced with respect to the required amount of resistances. Now whenever the capacitor is going to the upper plate is going to be shifted either on right hand side or left hand side, the values of C1 and C2 will change. That's why they are shown as variable capacitance in this figure. So as the values of C1 and C2 is getting changed, the bridge will be unbalanced in that case, and the resulting unbalance can be detected in terms of change in voltage between these two nodes. So if a voltmeter is used, what is the uh, change due to a particular displacement of the upper plate, that can be predicted in terms of the change in voltage. So here as well, the displacement is converted into change in capacitance, and later on, using this sort of an arrangement, the change in capacitance is uh, taken with respect to the change in voltage. Now for the other type of differential arrangement, the upper plate and the which is shown in this figure B, that is based on the variable distance between multiple plates. So for this sort of arrangement, the upper plate and the bottom plate can be considered to be fixed, and the plate which is located at the middle, it could be considered as the movable plate which can move in the vertical directions, and as it is moving upwards or downwards, the distance between the two fixed plates and the movable plate will vary accordingly and change the capacitance as well. Similarly, for this sort of an arrangement, the upper plate and also both the bottom plates are fixed in this case. Now if the dielectric material is moved back and forth along the horizontal direction, then that will change the relative uh, permittivity between the upper plates and the lower plates, and eventually cause in the change in capacitance. So similarly, they can be also coupled with AC bridge circuits, where finally the change can be uh, observed with respect to the change in voltage.
Sir,
Yes,
among those arrangements, which one is better and which one is have more effects?
they could be. I mean, the advantages can vary from application to application. So for different type of uh, applications, one design might be advantageous, whereas for other type of application, the other one can be advantageous.
Thank you.
Now, lastly, today I would like to just elaborate a little bit more on the differential arrangement which can be formed with respect to the change in distance mm, between the plates. So like I was saying that there are two fixed plates. Suppose one is P1, another one is P2, and there is a movable plate that is located in between them. So when the movable plate is at equal distance, suppose at equal distance d with respect to both the fixed plates, then when some voltage is applied and the movable plate M is located at the center, then both the capacitance will be equal, C1 and C2. So for that particular case, the voltages which will be developed between C1 and across C1 and C2 will also be equal and eventually result in the differential output to be zero as well. Now for C1, the voltage across so C1 is suppose the capacitance between the movable plate and P1. So that is represented here as C1, and the capacitance between the movable plate and the other fixed plate is represented here as C2. Now with respect to the capacitance values, the resulting voltage across the two capacitors C1 and C2 can be written in this form. So you can relate them in this way actually, like a voltage divider rule. If you consider the mm, reactances, so if you write in the form of voltage divider rules, you can later on simplify them to have this sort of an expression. So as the both the capacitances are equal when the movable plate is located at the center, then the voltage drop across both the plates will be, both the capacitances will be same, and that will result in zero potential difference uh, uh, between the two developed voltages. Now whenever there is a slight deviation of the position of the movable plate M, suppose if it is moved upwards by a displacement x, then if it is moved upwards, then the distance between the M and P1 will decrease by x, that is, and the capacitance, corresponding capacitance C1 is represented like this, and the C2 is represented through this expression, and the distance between M and P2 is increasing by the amount x. Now with these expressions, the uh, induced EMFs or induced voltage or developed voltages across both the capacitors E1 and E2 can be rewritten in this form. So just in case of C1 and C2, if we put these expressions, finally we'll have these two forms of the voltages E1 and E2. Now from here, if we take the differential output uh, in the form of E2 minus E1, so that will eventually give us this sort of a relation where the differential output delta E is actually proportional to the displacement x, because both E and D can be considered to be fixed for a particular arrangement. Now, as we are getting the differential voltage to be Ex divided by D, now the sensitivity of this sort of an arrangement can be predicted as delta E divided by X, and the sensitivity can be determined for this sort of arrangement to be the ratio between the applied voltage to the distance between uh, the plates during the null position. So this is one of the cases of differential arrangement, and you can establish a relation between the differential output and uh, the sensitivity. And there could be other arrangements as well, where instead of only 3 plates, there could be multiple plates present, and with respect to that, the capacitance expressions for the induced EMFs can also be developed. Now, in the later 2 slides, there are some advantages and disadvantages and some applications of capacitive transducers I mentioned. So for today, I think the time is over for the class, and I'll leave this to for your self-study. And later on in the next class, we can start our discussion with optoelectronic detectors or optoelectronic transducers. So what is the time? It's 11:43. You have a class after this?
Yes, sir.
Okay, then I should conclude here today. Now, if you want to ask any question. Do you have any quiz today?
Yes, sir.
Which subject?
Sir, signals and systems.
Okay, so how is your preparation? Or you were taking preparation during the class? Okay, no problem. In Saturday we have our quiz, so the quiz will contain questions in the form of suppose multiple choice questions, or there could be some short questions, and a small mathematical problems might be there, where you have to solve the problem and put the answer in a text box or something like that. So in Google form, I will uh, uh, take your quiz, and for each multiple choice question there could be one or more than one correct answers, so you have to answer accordingly. And if there is any small mathematical problem, now you have to solve it by do the calculation separately, and in the uh, form you have to put the answer, or if some other thing is indicated to uh, I indicate you to write something else regarding the mathematical problem, that you have to mention over there. And there could be some fill in the blanks or short questions that you can type in answers for those. So that's it for today.
Sir,
And
in the quiz, will you give the questions section wise, or will you give the all the questions at the same time?
the quizzes will be held at the same time for the 3 sections, right?
No,
But
sir. No, sir. He meant that will you give the question in the same page, or there will be separate pages for separate questions?
no, I have created 3 classrooms in the Google Classroom, or there are 3 classes for the 3 sections. So I'll post the, I mean, links of the form over there. So there might be some changes section wise in the question, or there may not be. However, I'll post the links of the Google form in your respective classes. From there, you can uh, access the question actually. So I'll not be posting through email or some other means. I'll post it in the Google Classroom. So from your respective accounts, you will log in and give your quiz. So there might be some changes in section to section in the question pattern.
No, sir. Sir,
So
I was saying that for a like for section B, there will be one single Google form. So you will give the MCQ questions, short questions, and math question in the same page of the Google form, or there will be multiple pages in the Google form, so that we have to go next and next pages to solve MCQ math questions or short questions, or will you give all the questions in the same page?
oh, you mean whether I'm going to create separate sections for each question or not? I mean,
Yes, sir. Yes, sir.
you have whether you will be able to see all the questions at a time, or you have to go one by one.
Yes, sir.
So that I haven't decided yet, but that that might be done as well. So that you have to answer one question, then press on next. So that might be done as well. So uh, that's not your concern, but as long as you are giving the quiz by yourself, you don't need to bother about those things, how the question is structured. But if the question is set in a way that uh, you will be able to view one question at a time, then I would suggest you to keep the time in mind. So do not waste too much time in single question. I'll mention how many questions are there. So with respect to that, you can uh, distribute your time. So if the question is given section wise, that you are going to view one question at a time, then if you waste too much time in one question, then maybe you'll not be able to answer all the questions. So yes, whatever you ask, that the question might be set in that way. So uh, depending upon that, you have to adjust your time. So just take the preparation. Don't bother about the question pattern too much, because if you're giving the quiz by yourself, then and you are well prepared, you'll be able to answer in whichever format the question is given to you. And I would suggest you to go through all the derivations and uh, all the mathematical problems. Although I'm saying that the quiz will be of MCQ type. However, your midterm is near as well. So if you study everything now, then it will be better for you. And also, if there is some questions regarding some portions of the derivations, uh, or some portion of the maths or the examples which I suggested you to go through, so you will also be easily able to answer those questions as well. So anything else you want to ask? Okay, so I'm concluding to this today's class.